Okay, this is where we left off. So I mentioned selection on survival, and then was there's also, so in other words, selection on survival is how well an organism, an individual actually survives with the traits that it has. Remember, you're kind of dealt the hand that you're dealt. In other words, you can't decide, oh, I want to throw these cards in and get some new ones and change my phenotype. But there's also selection on what's called fecundity, and that means how many offspring you actually produce. And then finally, there's selection on, well, sexual selection, and it's how well you find a mate. And in general, males compete with females, not entirely though. With humans, it's both. Are competing, females are competing with females for access to males and vice versa. Okay. So the first thing I want to cover is what's called modes of selection. The first one is called directional selection, and we'll go through examples of that where favors one phenotype. So anybody remember what a phenotype is? What is it? Right. Good. Okay. So phenotype is the physical manifestation of the genotype as it interacts with the environment. And then a genotype is actually the alleles that you have, or an individual has. Okay, and a good example of directional selection is smallest to largest. So we're going to go through all of these: stabilizing, disruption, negative frequency. But this is basically what it looks like. Okay, so just to look at this, here is the phenotypic measurement. Let's say something like hair length in wolves. Okay, goes from smallest to largest. And then here on all of these is the number of individuals. So we're first going to look at what's called directional selection. Okay, and here we say okay, and then this is okay. Now, this is what's called a normal curve. Okay, this is number of individuals. So most individuals are closer to the center. This is the average, and we'll say that's 6 inches for the hair length, and then 0 up to 12. Okay, so in these wolves that we're looking at right now, most individuals have an average hair length of 6 inches. Now, there's going to be, the thing is, that's the average. So there's going to be some that have 5 inches, some that's going to have 10, some that's going to have 7, some that's even going to have 3, let's say, a mangy one, right? So, but the average, if you add them all up together and divide by the number there are, is 6 inches. Okay, now, we're going to impose selection on this group. Selection on survival. And we're going to say that the weather, or rather the climate, is going to get colder. Okay? So, individuals, if it's going to get colder, who's better off? Individuals with longer fur length or shorter? Good. Okay. That means shorter is going to be selected against. And so, we're getting rid of all these guys. And okay, I'm going to draw another curve right here. And instead of, now the average is going to be 10. Okay? The average before was right around here, 6. So, first of all, the individuals who were, let's say, less than 6 inches, they didn't leave any offspring. Only those with longer fur actually survived. And then they reproduced, and now we have a distribution where the average individual has 10 inches of fur instead of 6. That's directional selection. Now, okay, here's the 10 inches again, right? Now the weather is going to go back to getting warmer again, like global warming. And individuals with heavy fur coats, they're going to be uncomfortable. Individuals with lighter fur coats are going to be doing just fine. So now there's going to be strong selection against individuals with longer fur coats and favors individuals with shorter fur coats. So, get this. And these are the individuals that are actually breeding. And now, the remaining individuals breed, and now we're back down, and it's actually an average of 3 inches. Whereas before it was 6. And then longer, it was 10. Okay, that is also directional selection. Whether it's shorter or longer means that it can be directional selection. Okay? Some people think, oh, it's different. No, it's the same sort of thing. So here's an actual example. First of all, here's a selection event. There was a drought for these Galapagos finches, and it reduced the seed availability. And the drought started sometime around here. And this is the number of finches that survived, and they plummeted, okay? Now, the beak size on these things is highly heritable. There's variation, like we talked about, so you need variation, heritable variation, and then you need something that differentiates among individuals that survive better than others. So, and then there's something called the response to selection. Now, to show heritability, this is the midpoint bill size, and this is the offspring bill size, and you see that there's heritability of 0.9 out of 1. So it's highly heritable. In other words, you inherit the beaks that you get from your parents. Now, in 1976, when the drought started, this is the mid-parent bill depth, and it's shorter and less thick than later on. After 1978, when the drought finished and there were more seeds being produced, then the bill size went back up because thicker bills were no longer needed. Okay, so it went up to the point, and then after this it actually went back down again. And if we actually look here, finches hatched in 1976, the year of the drought, or the year before the drought. The mean is right here, 1, 2, 3, 4, a little beyond 4. And then we actually look here. Oh, that's not, okay, 1, 2, 3, 4, 5. That's 2. 1, 2, 3, 4. So it's about 8. And then it changed. The ones after the drought, in other words, there was strong selection on having a thicker bill during the drought, because it turns out there's all these different seed sizes, and the only ones that were left, the first seeds that were being eaten, were smaller seeds and medium-sized seeds. The only ones that were finally left were really hard, thick seeds that you needed a thick bill to actually be able to crack. So only the birds with the thickest beaks actually survived. And here's, it went up to 9.8 millimeters. And so I want to show you right here. By this time, there weren't very many birds left. If we actually look, originally there were about 1,400 on this little island, and it went down to about 200. Most of them all died. In fact, there was a preponderance of males compared to females, because males have thicker bill size. Okay. So this is an example of directional selection, going to thicker bill size. Now, when the next year, when there was actually a lot of rain, there wasn't a drought anymore, all these plants were now producing all kinds of different size seeds, and there was now selection on actually having a thinner beak, because you could actually pick the seeds easier than with a really thick beak. So this is directional selection. This was a long-term study by the Grants, Rosemary and Peter Grant, and their grad students. Now, there's a different kind of selection where there's selection actually against the extremes, whether it's small size or large size. Okay? First of all, this is percent of the population. This is the birth weight in pounds. And then this is mortality, and which is the red stuff. So the red, there's high mortality at very small birth weights and very high mortality at low birth weights. That means all these individuals over here, and there's selection favoring medium-sized birth weights, which is right here. Okay? So let's think about this in terms of birth weights. What's likely to happen? Why is a small baby at a disadvantage? Anybody? All kinds of different problems. They don't develop properly. If they're preemies, obviously, their lungs aren't very well developed. They can suffer all sorts of, well, in general, larger babies have more resources. They're doing better. Okay, so there's strong selection, obviously. Any baby that's born, I think the smallest birth weights now are like 2 pounds. But the average is about, 6 or 7 or 8. Now, what about really large babies? They're doing really well, it would seem, but what's the problem with really large babies? Overweight, okay. But why would that be bad for them?
You won't have enough food.
Okay, think about a baby that's born at 15 pounds. What's going to happen with a mother? Yeah, exactly. Okay, so the baby may be fine, but the mother ain't going to make it. And even if she does make it, she's going to hate this kid for the rest of its life, right? For putting her through all that pain. So this is what's called stabilizing selection. So again, here's our normal curve. And we've got some size issues right here, right? Number of individuals. In this case, selection is coming from both sides. There's selection against these individuals, and there's the selection against these individuals, and all you've got left are these. So the next population is actually going to be right around, very tight around the mean, or the average. Now that's called stabilizing selection, the example I gave you with birth weight, but there's all kinds of other ones. In fact, probably stabilizing selection is where most populations are at unless there's a change in the environment. Okay? As they get better and better adapted to the environment that they're in. So you can start with the wolves again, and you find that eventually, if it doesn't, whether it doesn't change or the climate doesn't change, eventually there'll be more and more individuals that are closer to the mean. Okay. Now, there's another kind of selection. It's called disruptive selection. Here again we have bill depth, lower mandible width, and anywhere from, about 9 up to 19. Okay. You can see where selection is. Selection is killing all, actually, it's all this stuff. And the only thing that's left over are those birds at 12 and 15. And that's because In this case, there's actually what's called a bimodal distribution. That means there's two means, right here and right here. And again, it's going to be based on seed size. It turns out that there's two different kinds of seeds. There are hard seeds or soft seeds and smaller seeds. So you either have a wide bill to be able to crack the hard seeds, or you have a narrower bill that lets you get at the soft seeds that are smaller more easily. So let me show you again. Here's our distribution. Now there's selection against individuals who are in the middle in terms of seed size, or in terms of bill size. The ones that are in the middle, they don't have an advantage with the big seeds, they can't crack them, and they don't get at the small seeds as well and efficiently as those with a small bill. So those with a medium-sized bill are getting outcompeted by all the other ones. Okay, so this is okay. Disruptive selection. Okay. Now, there's another kind of selection. You're not really going to be responsible for this, but I want to give you an example. There's something called frequency-dependent selection. And the number of individuals determines who is favored and who's disfavored. So with positive frequency dependent, this is negative, but with positive, let's say there's individuals who have a hair length of salute of, let's say, 6 inches, but individuals with longer hair have a selective advantage, and they're going to leave more offspring, and the next generation is going to be 8 inches and 10 inches and all that. Okay. Now, negative frequency dependent selection is different. It means that individuals that are rare are at an advantage. Now, this is pretty cool. Okay, in the Great Rift Lakes of Africa, like Victoria Lake and Tanganyika, and another one, there are these fish called cichlids, and there's a species swarm of fish, and one version is that there's a lefty and a righty fish, and what they do is they come up behind this fish and they grab a piece of its scales. Now, you and I are lucky because we have a neck. But a fish doesn't have a neck. He can't look around to either side, right? So he doesn't see what's coming. So if there's a lot of right mouth fish that come up from the left-hand side, this guy, the fish that's getting the scales taken becomes aware of that, and is more favored to look for fish coming from that side. That means fish coming from the right side, with the mouth pointing left, actually have an advantage because they come up and there's kind of a blind spot for the fish getting his scales eaten. Okay, so as they become, now they're favored. That means they get a meal more often because they're rare. Well, those individuals leave offspring that are left mouth, and they become more common, and the other ones become less common, and it goes back and forth. So, where am I? Okay. So this is left mouth individuals. Over here is, we'll say, right mouth. But as left mouth individuals are common, their actual fitness goes down, and right mouth becomes more common. So here's the right mouth individuals. And it goes like this. Okay? Another good example of that is with salmon. Anybody ever go salmon fishing? Okay. Everybody like to eat salmon? Okay. Anyway, salmon have this this lifestyle where the fry are born in the stream. They hang out there for about a year. Then they swim out to sea. They hang out in the ocean for about 3 or 4 years, and then they come back and breed in a natal stream. And then they die. Now, that's the normal salmon. But there's also these salmon called jack salmon. They're smaller. They actually come back every 2 years. And obviously in a big fight between two males, the biggest male is going to leave the most offspring because he'll chase the other one away as the female lays the eggs. But a jack salmon isn't going to fight another big male. A jack salmon is going to hide behind a rock next to the female who's digging a red to lay her eggs. And as two big males are finding it out, he's going to sneak in, he's going to release the sperm, fertilize the eggs, and leave offspring by being sneaky instead of being big. Right? In other words, bigger, or survival of the fittest, or the strongest. In this case, the strongest is the smaller guy. Now, the trouble is there's limited spaces for those small guys to hide. So when there's only a few of them, they have places to hide and sneak in. But if there's lots of them, there's not a place to hide, and they're at a strong disadvantage because obviously they're not going to get into a big fight. So what you see is, you see these two forms that are each, the big ones, the big males have an advantage because they'll leave more offspring because they can fight everybody else away. And the small ones have an advantage, but only when they're rare because they have places to hide and can sneak in. So the same sort of thing happens in terms of these two different forms. Depending on how many of each size class there are, big or very small, that governs how their fitness is. If they're rare, in other words, there's fewer big ones, being big, and there's lots of small ones, being big is better. If there's few big ones, but lots of little ones, it's the other way around. The big ones have the advantage. They're not going to be fighting each other because there aren't that many of them. But the small ones won't have any hiding places. So this is called negative frequency dependent selection. Um, okay. Okay, so we've been talking about survival for the most part, selection on survival. Now the same thing happens, can be with fecundity too, how many offspring you leave. But then there's another one, it's called sexual selection. And the sexual form of selection depends not on a struggle for existence, in other words, let's say survival, but on a struggle between the males for possession of the females. Now, we'll see why it's usually this way and not the other way around in terms of the females struggling for males. But the result is not death to the unsuccessful competitor, but fewer no offspring. Now, secondary sexual characteristics include, these are males, actually, the showy feathers or the big racks of this Irish elk. That if you looked at these characteristics, if you had feathers like that, do you think you would fly very well? No. Also, who would you be very visible to? Huh? Predators. Okay. So why would natural selection actually favor traits that would reduce your survival? That's what Darwin thought. That's a real conundrum, right? Similarly, you have a big rack like that, and it was huge. It was, well, look at, there's the guy who's, let's say, 6 foot tall. I mean, this was a monstrous individual, much bigger than the elk we have today. And with a rack like that, you could fight other males very well, but it might actually give you some problems, like getting hung up in the tree limbs as you're walking around. Okay? So what we have is, we have traits that might be a disadvantage in terms of survival, but they're there. And why might they be there? Well, with a big rack, a bigger male and a bigger rack are more likely to win battles with other males. Or if it's female, what's called female choice, the male that has showier characteristics that get the eye of the female are the ones that get the mates, even if they don't survive as well. In fact, if they do survive long enough to mate, it shows that they have a pretty high quality. Because if they have a low quality and they're not good at getting away from predators, they're going to be eaten before they have a chance to mate. So there's two forms of sexual selection. There's intersexual selection. That means between males and females, and the female chooses which male she wants to mate with. And then there's intra-selection, where there's male competition, males against each other. Now with humans, the dominant form, it depends on culture. Let's say you live in Afghanistan. It's a very heavily male-dominated culture. Women have no rights. They're stuck in a little hut because their husbands are afraid that if they're not locked in, they'll mate with someone else. Okay? But here, as we know, males and females both get jealous. And so there's actual selection on both sexes. Females competing for males and males competing for females. Okay. Okay, so that's intersexual selection. That means two males of the same sex, right, are fighting each other.
I have a question on that.
Yeah.
I just want to know, out of curiosity, do they fight in the water or did it
Anywhere.
just happen? Okay.
Doesn't matter. They just happened, and that's probably the Yellowstone River, and just so happens. Now, so during the rut, that means when the females are receptive and fertile, this is in the fall, the males establish harems. The strongest get the harems. In other words, they get a bunch of females, while all the other males are on the outside looking in, wanting, right? Now, during the rut, by the way, the male who obviously has the females, has the harem, well, he's so busy either having lots of sex or fighting off other males that over time he tends to wear down. And so during the rut that might last, let's say, a month or a month and a half, oftentimes a male will be a harem male for a couple of weeks and then he gets tossed because he gets worn down. He doesn't eat enough. He's having sex all the time. How can you eat when you're having sex? I guess you could. And he's also fighting. Fighting and, right, F and F. Okay. Now, the question is, why does sexual selection exist? And what does Arnold Schwarzenegger and a male toadfish have in common? Huh?
They're trying to show off. Trying to show off.
Trying to show off? Okay. That's true. Anything else? Yep, got that. How about they both produce small, cheap sperm? Okay? Now, because, and the females produce fewer, larger eggs. Okay? Because there's variation in size and number, there are different selective forces on mating success for the females versus the males. There's an asymmetry, in other words, they're not equal size eggs, right? They're different size eggs and, or sperm rather, gametes, large and small. That means there's an asymmetry in gamete size, creates an automatic conflict between the reproductive strategies of the sexes, and this is why. Females' reproductive success is usually limited by resources invested in the large eggs and also in the offspring, if females provision the offspring, like humans do, right? So the females is usually, for humans, only have one egg, and then there's lots of sperm. Now, with the sperm, mating success is limited. So for females, mating success is limited by the resources that she can put towards her offspring. With males, small inexpensive sperm, there's lots of them. Who cares if a couple of thousand or a million sperm die? No big deal. It's not like you're going woo-hoo-hoo over sperm. You know, we kill them all the time. Okay, but what is limiting male reproductive success in this case is the number of females that a male can inseminate. Now I know that sounds sexist. You know, why is the males are the ones that should go around and mess around and females shouldn't? Well, it turns out actually that females mess around too, because oftentimes they're competing. There are males, they're trying to hold the males close at hand. And so the males actually, the females are looking for the best male. Let's say you have two birds that decide to breed together, a male and a female. They build a nest, females lay eggs, the young hatch, and they're provisioned by both parents, the male and the female. Now, right next door is another territory. So here we have this male, his name is Harold, and the female's name is Nancy, Harold and Nancy. And right next door, there's another territory, and his name is Raymond. And her name is Alfalfa. And it turns out Harold is kind of a bum. Not a bum in the fact that he's always wandering around trying to get extra pair copulations. He's just a low-quality male. Okay? But because Nancy is a low-quality female, they both have a substandard territory. But in the better world, Nancy, it would be better if Nancy actually had sex with Raymond on the other side, because he's a high-quality male, and then get Harold to raise Raymond's offspring. Okay? Now, so the female actually has a reason to mess around. So she still is going to have sex with Harold just to keep him happy so that he'll raise the offspring with her. But in reality, she's shopping for the best male sperm out there. Okay? So we often see things where females actually mate with a number of males at once for all different reasons, including differences in male fitness and also differences in compatibility, genetic compatibility. So, if we actually look, remember I said that females are limited by egg size and number. So, here we have least successful, most successful. And you can see that most individuals, this is a number of individuals, most females have smaller number of eggs, but some actually have larger numbers of eggs, but number of those individuals is smaller. But if you actually look at males, most males are losers. In other words, all these males up here, they're not getting any. Okay? It's only these few males that are inseminating all the females. It's kind of like, let's see, what was, when I was talking about earlier about who lives and who dies, I said there's one male in here who is the best, even though he dies at 21, because he's fighting and having lots of sex, but he's inseminating most of the male or females. Okay. You can watch this on. Now, the thing is, there's all different kinds of mating systems in animals and plants. In the one we just saw, that's called a male that mates with lots of females. It's called a harem system, like with the bull elk, but the males don't fight each other here, they just display. There are also some birds that have serial monogamy, like I was saying, Nancy and Harold. There's also some systems where male or females mate with lots of, a female mates with lots of males. Now, with humans do all that kind. There are certain humans that the Sultan of Brunei has a harem. Lots of women go there to get, well, to have lots of sex, and he's rich and he might give them things. There's serial monogamy, like most people. There's also even a case where there's one female and a couple of males sharing the female. But it's going out of style, but it's mainly in the Himalayas at the high altitudes where it's just too expensive, and you need two males to actually provision a female. So, with humans also, there's intersexual competition among the males against each other and the females against each other because they both provision offspring. So there's intersexual mate choice also, in that males and females decide who they want to mate with of the opposite sex. You have all these different mating systems. Some are more common than others. And then there's sexual size dimorphism. Males are generally bigger than females. So females are usually continuously receptive for sex. That's unlike most other female animals that only come into reproductive condition once a year, let's say. So like those female elk, they only enter estrus once a year in the fall. Whereas with females, they ovulate only once a month, but they're still receptive to having sex all the time. Of course, females have these sexual secondary characteristics, include permanently enlarged breasts. Other mammal females don't do that. And big butts and all that. Waist to hip ratio. They also have generally less body hair. And they have a high, sweet, mellifluous voice to entice males. Oh, so beautiful. Okay. Now, males, instead of concealing ovulation, they don't do that. They just conceal their feelings. They have sexual secondary characteristics, a big V-shaped torso with broad shoulders, lots of muscles. Muscle definition, instead of a high, sweet voice, they have a low grunt. Kill! And they're also hairy and aggressive. Okay? So, it turns out all you guys in here, you're all doing both. You're trying to get mates, and you're trying to fend off rivals. And I'm surprised there hasn't been a fight yet in this classroom over one sex or another. Okay. I'm going to... there's going to be homework for Top Hat, so there'll be new Top Hat questions available. I'm going to close the old Top Hat if you haven't already answered. Okay, class. I didn't get this far, but we're going to go a little farther because we got to cover some ground. So, we talked about Darwin's first great idea, which was evolution by natural selection, including sexual selection. Okay, and we saw how there's different kinds of selection. These are all hypotheses that have lots of support for them. So Darwin's second great idea, and well, they were both great ideas, doesn't have to be first or second, and also Wallace later on, was descent from a common ancestor. Okay, just like you're descended from your ancestors, your parents, your grandparents, your great-grandparents, and so on. So, the first question is, why do family members resemble each other and not look different, completely different? And as you can imagine, we all share genes, and the genes that we share from our parents are the ones we inherited from your parents. And it turns out, for each generation in sexual reproduction, you share half the genes that you do compared to all the genes that you have. So, your parents, you share half the genes with each of your parents. Okay? That's 0.5 or 50%. And then a grandfather, you share a quarter, because 0.5 times 0.5 is 0.25, and so on. Okay? Now, on the left, we look at our family tree, not an evolutionary tree, and we see some things that, like, the top is not your family tree. Great-grandfather, grandfather, father, you. Okay? Your real family tree is your great-grandparents, of which there are 8, and also second cousins. And then at each node, this is how far back it goes. And then the next generation, your grandparents, there are 4 grandparents, and I think there's 8 cousins or something like that. And then your parents and your siblings. And you both share, your siblings and you, your parents as common ancestors. Okay? So, now is the resemblance of relatives similar to the resemblance of species? Well, why do we resemble our relatives? Because we share the same exact genes by descent. That means inherited from our parents. Now, obviously, we're only sharing half the genes from each parent, so there's differences. And there's also, with sexual reproduction, there's some other shuffling going on. But it's because we share the same exact genes. That's why we resemble our relatives. Some more than others. Okay. Now, species are the same way. First of all, fish did not lead to salamanders, and then to cats, and then to you. No. First of all, there was a common ancestor of all vertebrates. Okay? And that was right here. It gave rise to all the different fishes, and there's lots of them. In fact, there's different, so there's sharks and rays, there's bony fish, a few other kinds of fishes that are as distinct from other fishes as you are distinct from reptiles. And then these fishes that are there, are also related to all these other things equally. So there was a common ancestor of all vertebrates, and it gave rise to fishes, and then later on to all tetrapod or 4-legged vertebrates right here. Okay, so this was the ancestor of 4-legged vertebrates that started out looking somewhat like a fish, but started developing limbs instead of flippers. Okay, and then a cat is a mammal. So right here, there was an ancestor that we shared that led to mammals, and also, since we're a mammal, also led to what? One of us. Okay, so it's very similar. Each of these different grades, from oldest to recent in time shared common ancestors. And they resembled each other primarily because they inherited similar genes, or the same genes. That's why we use the same genetic code. The difference in our alleles and those from bacteria, we share, well, I guess we share about 30% with mice or something like that. Okay? Now, why might descendants of either resemble their ancestors? Well, I just told you. Okay, we inherited alleles, the same alleles from our ancestors, or species from their ancestral species. Now, why are neither descendants or families of species or species identical? Well, there were mutations and there were changes that led to some of the differences. Also, which actual genes you inherited depends on where you got them from your mother or your father. And the same thing goes with species. The genes that a species might have inherited might depend on the ancestors that they inherited them from. So they're not identical. They share many features, but they also share new features that are derived, that have been affected mainly by natural selection. In other words, fit to the environment, adaptations that make them more likely to survive and reproduce in the environment they find themselves in. Okay. Oh. Now earlier, I laid out, and this is following mainly from that film that you saw, the video of Jerry Coyne, Evidence for Evolution, about what evolution is about. He said 5 points, and then he pointed out different predictions that you can make, and you should find these sorts of things if evolution by natural selection is actually true. First of all, you should definitely find in the fossil record, you should find origination and extinction in the fossil record. Now, you will not find everything in the fossil record. In fact, creating fossils is very, very, very difficult, and most things do not leave fossils. Like soft-bodied organisms usually don't leave fossils, but some do. But for most part, it's things with shells or bones or plants with, woody trunks and things like that are more likely to be fossilized. Okay? So, the fossil record is very incomplete, but we certainly find the origin of new taxa, like let's say mammals, and we always find them at a specific point in the fossil record. Like, we don't find mammals in 3 billion years ago. The only thing we find from 3 billion years ago in terms of the fossils are very simple bacteria, and that's it. Okay, it's only later that mammals actually show up, pretty much in the Triassic, which is billions of years later. Okay, now, and so for the same way with extinction, you can see when, like, there's no more dinosaur fossils any more recently than 66 million years ago. That's when they all went extinct from the meteor. Now, there's also things like homology, which means similarities that can be either genes or genotypes, what we talked about, or phenotypes. In other words, what they look like, how they act like, all that, because of common ancestry. So homology is always due to common ancestry. You can have similarity that's not due to common ancestry. We'll get to that later. But for now, homology is why species resemble their ancestors, just like we resemble our our parents and grandparents. And those similarities are inherited similarities. So like we have 4 limbs, that's why we are more like other 4-limbed vertebrates, amphibians, birds, a bunch of different reptiles, mammals, than we are to fishes, which were originated much earlier than the 4-legged vertebrates. There's also embryology, and as we'll see, we'll go through all of these. We'll see embryological development. So it turns out all vertebrates show that at a certain stage they have gills. If they're a fish, that's as far as they go, and they're actually born with gills. If they're a tetrapod, well, those individuals generally, they all lost their gills. Tetrapod, that's 4 limbs, and they're using lungs instead. Okay, but we still in embryology, we see that. We see vestigial traits. That means the remnants of traits that were once functional. Like snakes, of course, don't have any limbs anymore, but they're descended from a reptile that did have limbs. In fact, they share a most recent common ancestor with lizards that had limbs. If you actually look at the bones of a snake, you'll see there's a little area where there were actually the girdle of the pelvis and the remnants of legs, and then further up, remnants of arms. Okay? So those remnants are the vestigial traits. And then there's DNA similarities. The more recently 2 species share a common ancestor, the more alleles and genes they share because of descent and inheritance. Also, descent from common ancestors affects how lineages evolve through time. So we're going to look at why certain things, why is there bad design? Why is there, in fact, absolutely, in many cases, terrible design? For example, why do humans choke? And then there's other things that we would predict from evolution by natural selection. In other words, also transitional species. And like birds, there was transitional species, namely bird-like dinosaurs. Dinosaurs that had feathers. In the fossil record, we can see that. And we can also see new species formation, whether in the fossil record or incipient species that are just now, taxa that are now in the process of splitting. And then distribution of organisms on Earth, that's biogeography. Why do we find kangaroos and almost all marsupials on Australia and not in North America, where we just have one marsupial, but we have mostly placental mammals? Okay, so that's what we're going to be covering.